In this video, we'll be discussing improper integrals in detail. So far, you have seen definite integral of this form, where a and b are finite numbers, meaning this interval ab is a finite interval. So this integral would basically represent the area under this function fx within this finite interval ab. Here x equals to a is its left boundary and x equals to b is its right boundary. Now what if I extend the idea of area under this function fx to the infinite interval? Now in this graph, I do have left boundary as x equals to a, but I do not have any right boundary. The area under this function fx is moving forever and forever. Now, how can we define this area using integral? I can write it as integral fx dx. Now, the lower limit of this integral would be a. The upper limit is increasing without any bound. The upper limit of this integral would be infinity. Now, how can we define this integral? We can integrate fx dx, lower limit as a, upper limit as t. So as t takes larger and larger values, using this graph, you can observe that the area under this function fx would become equal to this area, which is shaded in this green color. So I can say that this integral would be equal to limit t tending to infinity, this integral. So to integrate a function over an infinite interval, we consider the limit of integral as upper limit increases without any bound. So this type of integral, we call it as improper integral. Now, given an integral, are there any ways to identify whether it's improper or not? Now basically there are two conditions to check for. So the first condition says the interval of integration may be infinite, the way we saw in the previous slide, or the integrand, that is the function which is being integrated, may tend to infinity within the interval of integration. Now consider this first integral. The interval of integration is 0 to infinity, which is infinite. Therefore, this is improper integral using this first condition. Now consider this integral. The interval of integration is 0 to 4, which is a finite interval. Now let's check for infinite discontinuity. So my integrand is 1 by x minus 3, which tends to infinity at x equals to 3, which lies within this interval. Therefore, this is also improper. Now consider this integral. Over here, we have infinite interval 0 to infinity. Also, this function has infinite discontinuity at x equals to 0. Therefore, this is also an improper integral. So both these conditions are satisfied in this integral. Now consider this last integral. My interval of integration is 0 to 1, which is a finite interval. Now let's check for infinite discontinuity. My function is sin x by x. So let's evaluate the limit of this function at x equals to 0. So when I find limit x tending to 0 sin x by x, the value of this limit is 1, which is a finite number. Therefore, this is a proper integral. This is not improper integral. So you see that given any definite integral, one has to be very careful while identifying whether it's an ordinary integral or an improper integral. Now let's use the limit definition to evaluate the value of this integral. So this is also an improper integral because we have infinite interval 1 to infinity. Now we might think, since the interval of integration is infinite, so the area under this function 1 by x square would also be infinite. So let's have a closer look and evaluate the value of this integral. So we will use the limit definition, limit t tending to infinity, lower limit as 1, upper limit as t, dx by x square. This is equal to limit t tending to infinity. So the value of this integral is minus 1 by x. Now let's put the limits of integration. So I'll have minus 1 by t plus 1. Now as t tends to infinity, 1 by t tends to 0. So the value of this integral is 1. So you see that this is a finite number. So in this case, I'll say that this improper integral converges to the value 1. Now observe this graph. At t equals to 2, the value of area is 1 by 2. At t equals to 3, the value of area is 2 by 3. At t equals to 5, the value of area is 4 by 5. So as t keeps on taking larger and larger values, the value of this area is coming closer to 1. So using this example as a guide, we defined integral over an infinite interval as the limit of integral over finite intervals.